Yeah. All right. Hi, everyone. So today we are going to be finishing up chapter 20 in the effect. So we've been talking about regression discontinuity, and we're just gonna wrap this chapter up. So we left off last week, just before we started talking about placebo tests. So regression discontinuity when it's working, should close all of the backdoors, even backdoors that go through variables that we can't measure. Of course, this is all conditional on everything working the way that we think that it's working. And that means that the only thing that should be changing at the cutoff value is whether treatment is happening or not, or the level of treatment or probability of treatment. So we can test whether that is actually the case by running the regression discontinuity model on something that the treatment shouldn't affect. So anything we might normally use as a control variable should work here. And we've got an example here where we've taken the standard income and run it against mean age in household as well as mean education in household, both things that are control variables in this sense. And we can see that there is no noticeable jump in the mean outcome in either of these examples, and these are both indicators that um, everything is happening the way we think it is. Regression discontinuity is fine. We're not going to run into any issues with these particular um, analyses. One thing that is a note of caution is if you do a placebo test with a whole bunch of different control variables, you will expect to find some discontinuities just due to random chance. And that does not necessarily mean that you do actually have an issue. Um, so do be mindful of that if you're testing a whole bunch of things. So the next thing we're going to talk about is the density discontinuity test. Basically, this is another thing where we're making sure that our regression discontinuity is working properly. So for RG to work, we need a situation where people just on either side of the cutoff are actually effectively randomly assigned to the treatment. This means that the whole enterprise is very sensitive to manipulation. And manipulation can happen in two different ways here. So the first is that the cutoff value is set by whoever determines the cutoff value with the knowledge of who will be treated or not. So the example that the author uses is that if you have a coach determining who gets to make the team, um, knowing that his son can run a certain time, and he sets the cutoff like right above the time that his son can run, that is putting his thumb on the scales. The other option is that individuals may actually have some control over their own running variable value, and there's two different ways that they might have this. They might have direct control, so they can directly say, I will meet the cutoff or I will not meet the cutoff. An example is like a discount in the grocery store where, it's like buy five and you get a super huge discount. You know what the cutoff is. You know that you can meet it by buying five. So comparing somebody who buys five with somebody who buys four is not really super helpful there. The other option is that individuals might have indirect control, and this is much more common. And um, my understanding of indirect control is that essentially the individuals are able to change the probability of meeting the cutoff by, running extra hard to meet a specific time or in track and field, or, essentially pushing themselves or changing their circumstances ever so slightly in a way that doesn't guarantee that they meet the cutoff, but changes their ability to meet it. Um, does that sort of make sense as a an explanation of indirect control to you? you guys as well?
I mean, you could think of it like an IV, right? So you're taking their willingness to meet this cutoff, and
Mm,
then that's still not going to perfectly predict what you're doing, but kind of sort of gets in the
yeah,
direction. But yeah, makes sense to me.
cool. So with that last little bit, that indirect control, we can test to see if there's manipulation of the cutoff. And basically what we do here is we calculate the density distribution of the treatment variable. We allow that density to have a discontinuity at the cutoff, and then see if there is a significant discontinuity at the cutoff. We can also just do this visually, so you can check for significant differences. But if you plot the density distribution and look at it, there shouldn't be a really noticeable discontinuity right at the like centered value of 0. So this figure 20.15 here is an example of that where we really don't see any sort of difference in the density function right around 0. There is this fun little blip like over to the side, and I haven't dug into it, but I'm like, oh, I wonder what's going on there. But it doesn't actually matter for this particular analysis. So the last section that we have is how the pros do it. So the first thing that was talked about in this section is something called regression kink. And basically, this is just sort of expanding our concept of what regression discontinuity is. So far, we've looked at discontinuity in the mean outcome at the cutoff, but we can look at a change in pretty much anything we want here. The most common alternative to looking at the mean of the outcome at the cutoff is looking at a change in the slope. So basically is the slope of the relationship, is the nature of the relationship actually changing at the cutoff? There are also cases where we might want to see if the treatment itself has a kink. In terms of doing the analysis itself for a regression kink, the code that we have been provided with in the book doesn't change very much. In the already robust package, essentially all you need to do is change this argument deriv to 1, and that's it. That's all you have to do. Um, An exception to that one very simple change is that sometimes researchers will also drop treated from the value, so they'll set their beta 2 to 0. One thing to note with changing what it is that you're looking at, whether you're looking at the mean outcome or the slope or whatever else, is that this will change your statistical power. This is particularly concerning when you're looking at changes in slope because estimating a change in slope requires many more observations than estimating a change in mean. So your statistical power is probably going to be of much higher concern here if you're looking at regression kink. The next thing that the authors talk about is multi-cutoff design, and these are where cutoffs might vary depending on a whole bunch of different factors, therefore providing multiple different cutoff values, or the cutoff values might change over time. Um, a common solution to having multiple cutoffs is to center your data and then just analyze it the same way that you normally would. Um, One thing to be mindful of if you choose to go that route, though, is that this changes the effect that you're observing from a local average treatment effect to the weighted averages of effects, which are weighted by how many observations are close to each representative cutoff. So you are looking at slightly different effects there. There are other approaches to multiple cutoff designs, and these are found in a package called RD Multi, um, which has a number of different functions, but one of these functions is the RDMS function, which allows you to analyze data sets where there is a single running variable, but there's multiple cutoffs within that running variable, determining different kinds or different levels of treatment. The other thing that we'll see here with multi-cutoff designs is situations where a treatment is assigned based on the cutoff of two or more running variables. And this sort of really complicates what um, our analyses look like at that cutoff because we're instead of looking at on the left here in this figure, we see we've got one vertical line that is our cutoff value, and our bandwidth is just two vertical lines on either side of that cutoff. It's very straightforward. As soon as you add a second running variable into the mix, we get this really complicated relationship where we've got, most of our values are untreated, and we only see this sort of like narrow subset of data up in the top right of this graph on the right that is actually treated. And basically, what this means here is that instead of having a single vertical cutoff axis, if you will. We have a vertical cutoff axis and a horizontal cutoff axis on a biplot, and we need to figure out a way to get our bandwidth to make this L shape that determines what the two different cutoff values are. So RDMS, the function that we just talked about in the RD multi package, does does sort of look at these sorts of types of RD data sets. And the approach in RDMS is to pick specific points along this sort of L shape here and estimates what is essentially just a pretty normal regression discontinuity using the other running variable. And it does this multiple times. So it iterates over these uh, until you get enough points along that sort of L-shaped cutoff that you can get an idea of the effect and how it varies depending on where you cross the border. I did not have time to like actually dig into what's happening here, so um, I don't know the specifics of it. But essentially, for now, it's magic, and it does
Hmm.
do it. I don't know if anybody else has like looked into RDMS.
I have not.
Okay.
I didn't get that far. But like
Yeah.
I feel like the whole interpretation gets a lot more complicated as well because you have these three different groups of untreatedness.
Yeah.
Yeah.
Yeah, I'm not sure. I think, I mean, it is in the how the pros do it section, so the sort of usual caveat of if this is you, you have some reading to do applies. Um, so the last thing that we're going to talk about is sort of, I guess, less different ways to analyze and more just like more things to think about when you're running regression discontinuity. And the first is what to do when your running variables are not nice. So running variables theoretically should be very continuous and they should be very smooth. We do have two issues that arise with running variables pretty commonly. The first is the level of granularity. So we run into issues when the running variable is measured at too coarse of a level for analysis. And the second issue is non-random heaping. And that's when some values of the running variable are much more common than others. So for granularity, determining how granular your data can be while still providing you with reasonable results is a bit subjective. Um, what you want to be able to do is you want to be able to measure the variable precisely enough to distinguish um, which observations are comparable and which observations are actually not comparable. You also need something that is fine-grained enough to properly model the shape of the relationship between the outcome and running variable leading up to the cutoff. So this will take a little bit of just understanding your data, understanding what questions you're trying to ask, and trying to figure out whether your data actually meet the criteria to be able to run RD. Um, One thing to not do is to try to solve the problem by clustering your standard errors on the different values of the running variable. This is another case where this was standard practice for a really long time, but it turns out that that's actually worse than not addressing the problem at all in many cases, so don't do that. The other issue we have is non-random heaping. And so basically you can see it here in figure 20.20 where we have really noticeable peaks of density of our running variable at certain values. This often comes in the form of rounding, so you can imagine that our running variable here is something like weight. All of the low values are values where people point to, or people indicated their weight as like 172.3 or 172 even, 173 kilograms, and then that's a very large person. I realize that. This is because I think of things normally that are much larger than people. Um, that's a normal weight for a male lion. Fun fact. Um, so yeah, you might have let's pick a more normal. So you might have some weights where these are um, 82, 83, 63 kilograms, and then all of these little peaks are the round numbers. So people are reporting their weights as 80, 85, 90, 95. Um, so basically what this will do if we have this non-random heaping is that we will get really highly influential values that are going to pull our estimate away from the true effect. So in the figure on the right here, the sort of standard RD plot, we've got our running variable. All of our non-heaped observations are in the black circles, and all of our heaped observations are in the white circles or the open circles. And you can see that there's two different relationships happening here. They have identical slopes, but the intercepts are different. Um, and that means that depending on what we're looking at, our our estimate of the discontinuity at the cutoff is probably going to be different. There's sort of two ways that we can address this. The first is to drop observations just around the cutoff value, so just around this sort of vertical line here in order to clear heaps. The author called this the donut hole regression discontinuity, and I think this is just his name for it, although I'm not 100% sure it might be the technical name for it. Um, However, further research has sort of shown that even if you drop observations right around this cutoff, heaping is still an issue if they're away from the cutoff. So perhaps a better way to approach this problem is to split the sample by whether it is a heap or not and analyze each side separately. So in this example, you'd kind of have two parallel analyses going. You'd have an analysis of all the black points and an analysis of all the open circles.
Could you just do this by including a dummy? So you could run it at the same time? Because otherwise maybe you get like into a problem of power. Yeah.
Yeah, maybe. I don't know.
Sorry.
No, it's all good. You should write the author and be like, hey.
You need to elaborate.
He'd probably be happy to. He's with all
It's
of his
true.
side footnotes.
Yeah, I
He,
liked the Run DMC reference in the side note in this
yeah.
chapter. All right, so our last section is all about dealing with bandwidths. And this is pretty straightforward. It's just that there's three main approaches to selecting a bandwidth. Um, the first is the non-technical approach, we'll call it that, which is you pick a bandwidth. Of course, it's a little bit more complicated than that. You're not just, throwing darts to pick a bandwidth. You're looking at your data, you're thinking about what makes sense as a bandwidth and thinking about why you would justify the bandwidth that you do select and just going with that. The second option is to select a whole bunch of different bandwidths, and basically you run a sensitivity test-based approach. So you select the largest bandwidth that you think makes sense for the research design, and then you start shrinking it. You estimate the RD model for each of those different bandwidth levels that you select and compare them. And then the last sort of option is I guess the most data intensive way to run this, and that's letting the data pick the bandwidth for you. So you have to select an objective of what a good bandwidth looks like, and then use your data to figure out how wide a bandwidth is the best one by whatever your criterion is. Some options for this sort of data-based approach to selecting a bandwidth include cross-validation and the optimal bandwidth choice approach, which you are welcome to read further about if they sound like helpful to you. I feel like selecting an optimal bandwidth feels like a similar problem to selecting the optimal number of bins or optimal bin width in like a histogram, where there's not really any one good answer of how you should do it. There's a lot of sort of decision making and thinking about it that has to go into it. And that is the end of the chapter.
Yeah,
So yeah,
really nice.
Yeah.
any final thoughts on chapter 20?
No, I'm struggling to see in my own life where I would be applying this. I think it's a really cool method. I just don't see it for me personally.
Yeah, I think you have to know about this and then watch politics change. I think like in political sciences, they really like Italy because they keep on introducing methods where they're like,
Huh.
oh, you're gonna get this thing if your income is so and so.
Mm.
Um, but yeah, I think unless you have like a really cool policy, it's hard. Which is one thought about this whole king thing, right? Like if you're, or no, I think it's called scrunching or something like that. Like when you're um people who are or like if there's a threshold and people can non-randomly select on which side they want to be, then like the RDD is off, right? Because you don't have the randomness anymore, but you can actually make a whole thing of it and be like, oh, well, people actually know about this. I think it's called something,
Mm.
I don't know, kink bunching, something like that.
That's interesting. Yeah, not
That's
familiar.
cool. Yeah, I mean, I guess in a sort of my side of things and in the sort of like ecology, biology, I could see something like this being useful if you're looking at like management or conservation actions. Um, so looking at like um, maybe a species is placed on the endangered species list in a certain year, and you could look to see if I would think it'd be more of a slope like regression kink here. look to see if there's differences in decline or um, in species abundance. So yeah.
Yeah, that makes sense because also like I mean the animals aren't going to sort into anything because they don't know about the whole
Yeah.
listing. That makes it a lot easier.
All right, so we have a half hour left. I can go through like roughly half of the next chapter because I didn't get through the whole thing, but if that makes sense, it might be easier to actually finish up entirely next week if we make a little progress on chapter 21. Is that okay with everybody?
That's fine with me as long whatever you feel up to is good with me.
Yeah, yeah. Again, I have about half the chapter ready, so it will be something.
Yeah, then let's do it next week, right?
What's that?
Wait, so you suggested doing it next week because then you have everything together, right?
Well, there's two more chapters left. So what I'm saying is if we go through
Ah,
some of chapter 21 today, it probably increases the chance that I'll be able to get
we'll
through
finish next week.
everything next week.
Nice. Then let's do that.
Yeah,
Yeah,
okay.
let's do it.
Yeah, good, good. Um, okay, sharing my screen. Can you see it?
Got it.
Okay. Yeah, so this will just be a brief introduction to chapter 21. It's the miscellaneous, one of the miscellaneous chapters anyway. I don't know under the rug exactly what we're going into. I haven't previewed that one yet. So this is called A Gallery of Rogues, Other Methods. And this chapter does not go deep into any of the methods. There's no R code, for instance, no how the pros do it. It's really just to whet our appetites about some of these methods that are out there in the wild. Has anyone looked at this chapter yet? Okay. I still think this will be interesting. Um, So, uh, yeah, just a couple introductory notes. Like these methods fall under a couple buckets. I think most importantly, these tend to be newer methods. So ones that are, new maybe within the last 20 years, as opposed to like regression, right? That's been used since what, the 19th century. Uh, they tend to be, really interesting or promising, but maybe are more technologically complex. So it's really hard to show you maybe the machinations of how these things work, right? And all this stuff's just kind of hidden behind and extracted away in a package. Um, and then some of these maybe are not entirely tested, like there's active research and maybe critique still going on to say like, is this a worthwhile method for a lot of use cases? So what we'll do just in our remaining time, or maybe even sooner, is just go through three different methods that are out there. The first one is synthetic control. I was curious, Sarah, are you aware of this method? Have you used this one in any of your
Yeah.
research?
Yeah, so actually I use it in like a master's something project.
Okay.
Um,
Yeah.
and like, I mean, the cool thing about it is you just have one treated unit and you can still do something about it, which is like, yeah, that happens a lot to countries mostly, that one country gets hit and then you want to know what would be the alternative outcome. So for example, Brexit has been studied a lot using SCM.
Oh, cool. Yeah, and just so you know, the other kind of free introductory causal inference book out there that's people cite the causal inference, the mixtape, has a full chapter on synthetic control. So if you want to dig deeper on that, there is some R code there for folks to check out. Um, so I have not used this method, so it's new to me as of reading uh, this chapter or portions of the chapter within the last couple of days. But from what I understand, this is kind of like DID, difference and differences, with a matching element to it. So the idea is you look at the pre-treatment period, and then you make adjustments, between the treated and untreated populations uh, using covariant matching. And so once you've controlled for pre-treatment differences, then you kind of look at the the post-treatment, kind of how things are playing out, the outcome, and measure the significance of the effect from there. And so, yeah, key points with this one is you are using covariate matching, not like propensity score matching, which is done via regression. For this to work, you do need a longish period. It didn't really go into detail about this, of pre-treatment data. The matching that happens on the pre-treatment period typically includes the outcome variable itself. And I think we saw a couple other techniques that do that. We're definitely not matching on the post-treatment period. That's something that was stressed, right? Because that's kind of like cheating. You're not necessarily cheating if you're matching the outcome on that pre-treatment period. And then finally, with this approach, you're typically not making like parametric assumptions with your models. It's running these placebo tests, right? So you're like, right, I guess with the placebo test, a lot of times you're just kind of creating an arbitrary time when treatment occurred when it really didn't, right? And kind of seeing the variation there versus what you actually witnessed after you did these controls, and trying to come up with, statistical significance there. So it's kind of like a randomization test or permutation test. If you're familiar with that, it seems to work in that manner. So kind of a non-parametric type test.
So it's actually not that you're changing the year where it's being hit, but I think you're like changing the country. So
Yeah.
you're
Okay.
saying
Yeah.
if we're talking about Brexit, we're checking out if it had
Yeah.
any effect on France.
That's a good point. I think I'm conflating some of our earlier placebo tests where we did move
Yeah.
the treatment period, whereas this one, I think you're right. Yes, you're kind of removing the treatment group and then just comparing different countries,
Yeah.
right? Because no two countries are going to be exactly alike. So that's kind of just establishing your baseline for what randomness looks like. And the one example they had in the book was in fact comparing countries, and there was a conflict, right? And it's like before and after. And the idea is there are weights being applied behind the scenes for your control group. And the key point with your control group is you generally have, multiple items at play that are getting weighted together. So in this case, different countries. And how this would work ideally is that you end up with this matching and weighting process, you end up with something that looks very similar to your treatment group pre-treatment. And in this case, this Basque County GDP before the conflict, look, I mean, it's the treatment and control are right on top of each other. And a point in the book was that, well, the conflict maybe started in 1970, but things didn't really, there's a ramping up period. So even though we just controlled for pre-1970, things still looked similar for a while afterwards. And then you see kind of a disconnect later on, a few years after 1970. So couple, pros and cons with this approach. It's not as reliant on functional forms, parametric assumptions that we tend to make with like regression, right? Differences, we have this parallel trends assumption that does not apply here, which is good. The author kind of just makes this remark that he considers this to be one of the most important innovations in causal inference in the last, I think as of when this book was written, I think in the last 15 years, so it's probably 20 years now. So still fairly fresh among some of the methods that we've been reviewing. Cons is that you do need a lot of pre-treatment data for this to work well, and it tends to so generally, again, you are fitting to this outcome variable in your pre-treatment period. There's a tendency to overfit. Not a lot of detail on that, but those were the two cons that I saw.
There's another con. If you're investing a country or a city or whatever, that's extreme, you can't do it because you need to make the synthetic control, you're averaging out. So if your country is above everything else, you can't make the average of that because it just doesn't add up. So you
Yeah,
need something that's somewhat average.
right. So I don't know, the canonical like statistical example where you're like dealing with like wealth, right? Or like how much people make in a year, and then you have Bill Gates in your sample, or like Elon Musk or somebody, right? And it's like, okay, this completely screws everything up. Because right, so that's a good point, right? If you have a pretty drastic outlier, you're not going to get something that looks like right that other country or subject that you're interested in.
Exactly. Like a synthetic control for Elon Musk is going to be really, really hard.
Yes, yeah, yeah. Okay, this I have a very brief overview on matrix completion. Anyone heard of this method? So again, this was pretty brief, and it seems like one of the canonical papers on this just came out within the last 5 years. But this, if you've ever studied recommender systems, I have a little bit. There's something called like collaborative filtering, which is, you think of like Netflix making recommendations for Netflix movies, and you have this huge list of users and a huge list of movies that they've liked. And so the idea is that you're trying to fill in the blanks for movies that certain users haven't watched before. Um, right. So you kind of look at similarities between other users as one way to do it, right? To fill in those blanks. Like, oh, you both liked Star Wars, therefore, this other person likes Star Trek, so you may as well. And so that's kind of how this approach works as well. They don't go into the mechanics. Um, and a lot of times what you're trying to do is figure out an average treatment effect on the treated. And I pulled in one of the graphics from the chapter. Let me just explain to you kind of how they set this one up. Kind of the straw man version of this, which is um, treatment. So you have two groups, like treatment and treated and untreated. Treated would be that you watched Home Alone in a given month, a Macaulay Culkin movie, right? And then the untreated group is you did not watch Home Alone. And then what we're measuring for these various time periods, time one, time two, and time three, is did you watch the movie My Girl within that same month, which is another early 90s Macaulay Culkin movie. And again, generally, you're kind of focusing on the treated population. So folks that did watch Home Alone. And so, right, and so we have 4 different users and three different time periods. You could consider those to be months. And so wherever we have these populated values for treatment, we're trying to figure out the counterfactual, right, what would have happened for individual 4 in time period 1 if he or she didn't watch Home Alone. What would be the likelihood that he or she would have watched My Girl? Um, and so the way they describe this method, um, yeah, so it literally is filling in these blanks here, and they describe it like it's almost like a two-way fixed effects model where you have different dimensions that you can look at, both like similarities across individuals, and then there's this time component as well, right? So those could be considered your two-way fixed effects. And I imagine the way these are completed is just some sort of matrix multiplication, because that's how a lot of the recommender system, non-deep learning methods work. Um, and this was not in the book, but I just wanted to point out, I just did a Google search that there is someone that's put together their own ML-based causal inference tutorial with kind of a homegrown, here's how you would implement this method. I'm pretty sure it's from scratch. Um, I did not spend a lot of time on this, but just wanted to point that out there, put that out there for you guys. And I want to just put the link here in the chat. So
Thank you.
yeah, matrix completion. Okay. So I do think that's cool. Again, borrowing from what to me looks like recommender system logic applied to causal inference. Any any questions on that? I know again it's very brief. Okay. So actually there's two more methods. I thought there was only one. Next one is causal discovery, which is a really cool topic. We spent what the first um 8 weeks of, of this book just going through um, DAGs mostly. Like, hey, it's really important to create DAGs and make sure you're considering all these relationships between variables. Causal discovery says, well, maybe I don't need to do that. If I have a really good set of data and I think that covers all the relationships, I can let the data speak for itself in creating these DAGs. I have heard of this, but I haven't really read much about it. I think you can, there's books out here that covers this kind of approach at length. Um, so there's two main things you need to do with causal discovery. One, determine if there is relationships between any two variables. And then once you've established that there is, like correlation between variables, then what is the direction of those arrows? And in the book, there is a reference to an algorithm SRS. I think that just the initials of the authors that created this algorithm. It sounds like it's a slow algorithm and there's better ones out there today, but this one is a good place to start if you want to go down this rabbit hole. And so what you basically do is you start with this idea that you have all your variables and you're going to make a fully connected graph, right? Um, and then you have an algorithm behind the scenes testing for significance between individual variables like A and C, for instance. And if you find no statistical significance, you drop that relationship altogether. If there is a relationship there, statistical significance, if you will, then you start dropping um, other variables in the graph, maybe one at a time or in pairs. I'm not 100% sure, um, how the algorithm works because they don't go into detail, but that's generally what you're doing and seeing if once you, if you control for other variables, if that relationship still exists. Um, if it doesn't, then you drop it, right? Because A and C could be related because of their connection with B, right? Like confounding variable. So that's the whole point there. And then you need to find the direction of the relationship. And this is the hard part with this method, and it's definitely not foolproof. Sometimes you can't get to the entire relationship just from this algorithm. But what it can find readily are colliders, right? So the example is A, B, and C. Um, if you're testing for correlation and it doesn't exist between those two variables, except for when you control for B, then that means there's a collider. And so, I'm just doing this very basic DAG relationship of what a collider looks like. And by filling in the gaps with these colliders, that sometimes can give you a definitive idea of how these other relationships work. But other times you don't always know, like are the arrows pointing left or are they right, up or down? It really depends on, can I solve a piece of the DAG over here? You're right, that gives you enough information to fill in the directional relationship in other areas. But my understanding is that in most cases that you still won't be able to find the full nature of the relationship in a complex diagram, but it's a good starting point. And with domain expertise, that it may be enough to get you going with a really good starting point for your DAG. So long story short, this is more of an automated procedure for creating DAGs. And my guess is that if you have a really high dimensional data set, that's probably where a lot of folks are starting with, rather than trying to attempt to ascertain all the relationships on their own.
That's really cool. Do you know if there's an R package for this?
I don't remember top of mind. Let's see. Go into the book here. I may just have failed to capture that. Yes. Okay, here we go. pcalc pcalg package in R and CDT in Python.
That's super cool. Nice.
Okay, and so last method we'll talk about here is double machine learning. This one's really cool. And he starts off by describing, how does a linear regression work, right? And assume the variable of interest is really X, or the relationship between X and Y. And so like the beta 1 coefficient is really what we're most interested in capturing. But there are confounders, and in this case, there's just two. Let's say we've, accurately identified a DAG. We just need to control for W and Z. So with a linear regression, you just plug those in as additional variables, covariates, and the hope is that's enough to capture the causal relationship between X and Y. But that's not always going to work, right? Because we know that relationships are more complex in the real world. There are interactions, non-linearities, and we've gone into the various techniques you can do to make an OLS regression more complex, but that doesn't always get the job done. And so there are a lot of machine learning methods that are really good at capturing these relationships, or good at prediction. And so the idea with this method is, we harness some of those tools, and it's really open-ended in terms of like what machine learning approach you want to use. But you may end up with essentially a better beta 1 coefficient, right, in this OLS. And so the author kind of goes into something we've seen before with an equivalent way to think about like an ordinary least squares, where you can just regress Y on W and Z, the two controls, and get the residuals from that, right? So leaving X out of that OLS. And then you can regress X on W and Z, the controls, and get the residuals from that. And then you do a regression on, this residual version of Y, residual version of X, and then you get your beta 1 coefficient. Do you guys recall that from an earlier chapter? It's the same thing as doing what we're seeing up here. Just it looks more complicated, but you effectively get the same result. But double machine learning kind of uses this form of doing regression, implementing its approach. And so typically you would have a data set, you split it, and the example that he uses, you would split it into two halves, and you would train, let's say, two machine learning models, like XGBoost, right, is a popular one for doing regression. And you would potentially just do two of these regressions, right? Like Y, the outcome regression on W and Z, and then your X on W and Z using XGBoost or something. So, there could be interactions and nonlinearities between all these variables. And then, like, anything that has a kind of a decision tree under the hood tends to do a better job at picking up some of these interaction effects and nonlinearities under the hood. And so you have these two models, right, that you fit on half of your data. Then you take the other half of your data. And so these models, you can get a predicted Y and a predicted X from the models. And then you calculate the residual, right, based on the other data set, the half that you've stored over on the other side, off to the side. So yeah, then you it's basically a holdout sample. You calculate the residual y, residual x, and then you can fit a standard linear regression to those two values that were predictions based on a complex machine learning method. So that, at least that's my interpretation of how this was being described in the text. So then you get potentially a stronger, more precise estimate of beta 1 because you've more accurately controlled for those other variables, right? The confounding variables that you're not interested in. And so one final complexity is that you would reproduce this procedure using the other half of the data to fit the model and then doing that kind of, the residuals and then fitting the ordinary least squares on the other side. So you'd have two beta 1 values and you just average those out. And so the idea was you get a strong, more precise estimate by doing this procedure twice, just using the half of the data in a different fashion each time you're doing it. So first time you're using, the half over to your left to fit the machine learning models, the data over to your right, you're using to do the simple OLS, and then you kind of reverse those two, what you're using those two halves for.
That's so
And
clever. I really like
yeah,
it.
I like it too. So it's, part of the problem with machine learning methods in general is that, right, they're great at prediction, but obviously not great for inference in a lot of cases. There can be black boxes. So this is attempting to get the best out of both worlds, where your ending place is an interpretable model like linear regression, but you're doing work, harnessing the power of machine learning prediction initially to get better controls or to block out those control variables, those confounders that you really don't want to influence your estimates. Yeah, so that's one half of chapter 21, and we're pretty much up on time. So I think that would be a good place to stop.